a distinguished engineer, CTO office at Extreme Networks, Mikael Holmberg, and his presentation on the myth around AI networks and AI for networks.
The myth around AI networks and AI for networks. So I'm going to touch on both of these, and there truly is a big difference between these. So the difference between AI for networks and AI networks is quite substantial. And as said, I will cover both in this presentation. Now, just imagine the amount of computation you need specifically for AI training models. And to put this into some context, GPT-3 have around 175 billion parameters, and it's unimodal, so it's only text. While GPT-4 has around 1.8 trillion parameters and do understand images as well, so it's multimodal. So to run these computations, you need an infrastructure including network storage and compute that supports all these demanded requirements. So this is the AI networks part. Now, if you then look at how you could utilize AI for networks, it could be adjusting parameters like Wi-Fi, RF, channels, channel usage, so on and so forth. Or think of the CSPs, so the communication service providers 5G networks, where we talk about network slicing, for instance, that will allow for specific parameters to be adjusted for a specific use case, customer, what have you. So this is kind of on a high level the difference here. I'm going to touch more on the AI networks part. I do believe that that's kind of hitting the audience more than AI for networks. We'll be talking a lot about automation here as well. Obviously, that's an interesting aspect and discussion as well. So how much is AI actually coming into play when you start to talk about automation? So let's take a step back here and kind of look at the different AI waves. So wave one, this was the first wave of AI that started within the research ecosystem back in the 90s and can be seen as the foundation of where AI evolved in the first place. The second wave of AI allowed access for HPC, access to software, and a broad expanse of network accessible data that has been widely enabled by the public cloud providers like Microsoft, Amazon, and Google. Wave three, now this is the big inflection point for AI, where it's entering the mainstream, claiming that it is going to revolutionize or the revolution will be hybridized. And this is also where enterprises are starting to evaluate how AI can be used to accelerate business and reduce costs. Now, in addition to that, this is also where the agentic AI is becoming the big next thing within AI. So wave four, this is the shift towards more autonomous self-learning systems and use cases with less supervision than the previous waves. And the industry has been working on autonomous self-driving cars for a decade. You probably all remember the kind of hype around 5G was the URLLC, so ultra reliable, low latency connectivity for autonomous driving. And we are now starting to see use go beyond the pilot stage for these the real world implementations and small scale deployments. So this is an illustration of a more comprehensive picture behind the just AI ops. So meaning that you start to talk more about platformization and with AI components like you have the core, you have your large language models, you have your RAGs and so on. In such a platform, you will integrate conversational, multimodal, and agentic AI into one network platform that would provide kind of the following functions, and those functions are basically listed there as three functions. I'm going to actually use the Extreme Platform one as kind of a real world example to kind of walk you through what this basically means. So the first one you have is the AI expert. This is the conversational, chat GPT like where you can talk with it. Then you have the AI canvas. And this is the interactive multimodal one that shows things like top users, top applications, And you can choose how you actually represent it. Is the pie chart, a graph, so on and so forth. And then you have the AI agents. This is the autonomous part where you tell what to do. So it could be human in the loop or without human in the loop. So if you put this into the context of automation, obviously AI is starting to play a big role here as well. How you automate remedy of issues, optimization of things within your network infrastructure. So as we probably all know, Ethernet was founded back in 1973. So it's a 50 plus years old technology, and it was founded by Bob Metcalfe. So those of us who's been in the industry for quite a while probably remember the CSMA/CD, carrier sense multiple access slash collision domain with the 10 meg Ethernet. Obviously, Ethernet has gone a long way since then. Ethernet is really not the same as it used to be. And you are now starting to talk about Ethernet in the AI age, where Ethernet speed has increased. We talk about 400 gig, 800 gig, 1.6 terabit in works, as well as 3.2 terabits. Now, kind of heading on the slogan here, the AI age for Ethernet, we kind of all realized based on my intro that to run those amount of AI workloads, you actually need to have capacity in your network. And with that, I will say basically your data center fabric needs to have capacity. Hence, as said, you start to see, 400 gig, 800 gig networks being deployed, mainly in the data center, obviously. Ethernet obviously also have a multi-vendor support at all layers, including switches, NICs, hosts, test equipment, and so on. It has a proven track record on link speeds, protocols, optics, cables, with truly IP scaling to any size and shape of network. So as said, different speeds as well, but it's far beyond just different speeds. So there's not much to explain about this slide. I think it's pretty self-explanatory. What it basically says is that the CPUs are optimized for serial tasks, while the GPUs are optimized for parallel tasks, and then the GPU clusters are for scale up of AI workloads, meaning that you integrate GPUs. So I'm trying to actually skim through this on a higher level, but there is a lot of details behind this, how you build these networks. I'm going to cover a couple of design architectures, which you can always then question which one is the right. You talk about rail designs, claw designs, so on and so forth. But to kind of, you know, put some details or expand a bit on this. So traditional data center traffic typically consists of many asynchronous flows. These could be database calls, end users making requests of a web server, and so on. AI workloads involve fewer flows, and they are by nature elephant flows, where majority of the data can be transferred between GPUs for extended periods of time, and they could be long-lived. Now, as opposed to traditional networking, the pod of a GPU requires all the data before it can actually move forward with its own tasks. So a group of GPUs must receive all the data before they can start their own job. These could be outputs from previous steps like gradients, model parameters, and so on that becomes vital input to subsequent phases. So this in turn means that huge flows of data among a mesh of GPUs, you will have fewer flows, which means less entropy for possible load sharing. So a lot of or a few flows, elephant flows, load sharing becoming more challenging because you don't really have enough entropy there. And since each GPU relies on all data from another GPU, any stalling of one GPU, even for a few milliseconds, can lead to a cascaded effect, stalling many others, making the job completion time critical as the entire workload then relies on the slowest path in the network. Then you have something called the tail latency. When a packet is missed or delivered out of order, and will introduce high latency. So to sum up here, a slower network will lead to slower job completion time. which means less utilization of the expensive GPUs. So as you can kind of see, the network part is truly becoming more and more critical when you start to talk about AI networks. So the infrastructure for actually running your AI workloads. So the AI workloads do present new challenges to current internet, as we kind of touched on already. And they are higher scale, higher bandwidth, multipathing, fast reaction to congestion, latency, so on and so forth. Now, this is an illustration of kind of a front end network or something you guys probably see in the data center claw design, a spine leaf design where you would have then a leaf layer where you would connect your or that's the attachment point into the networks, your servers connect in there, your hosts connect in there, storage connect in there, so on and so forth. But then you have the flip side of this one being kind of the backend network, where you now start to connect your GPUs, your GPU clusters, interconnected GPU clusters. And this is where you then start to look at various designs. Could be a rail design, could be a claw design. It's kind of up for debate which one is better based on basically what you want to achieve here. And then Rocky. So as we all know, the challenge with Ethernet is the nature of Ethernet. It's lossy light. It's lossy. And what you want to actually achieve is a lossless network. So ROCE stands for RDMA over Converged Ethernet, where you basically need to start to look at how would I transform my lossy network, Ethernet network, into a lossless network. So I'm going to touch a bit more on ROCE in the later slides. So AI workloads. So I'm just picking a few of the challenges here. Obviously, as you can all appreciate, there's going to be a lot of more of those. But AI workloads do pose some challenges, which are things like incast. This happens when multiple sources target the same destination. You have something called the oblivious bulk synchronization. So this is when the computation steps are interleaved with global communication steps that often synchronize processes. Now, think of an AI deep learning thing. You have a number of processes, you have the duration of the computation, size of communication, how many endpoints do you have? How many GPUs do you have in your cluster? I mean, we start to talk about, huge amount of workload, as I indicated in my intro here, talking about GPT-3 and GPT-4 with billions and trillions of parameters. Latency sensitive. So some workloads are latency sensitive. They could obviously fall into the previous category here. And then you look at the deployment characteristics for such. Confidential compute, all traffic must be encrypted on the wire. Multi-tenancy, need to manage thousands of such hosts or endpoints. Cost-effective low-diameter topologies require advanced load balancing and routing with high bandwidth requirements. So there's a bunch of obviously kind of hard challenges to meet here or hard requirements that you need to meet here. Now, UEC, Ultra Ethernet Consortium. So this is kind of the next phase of the Ethernet evolution. So a group of vendors and operators have teamed up to form the Ultra Ethernet Consortium. As I kind of indicated that there are concerns that today's traditional network interconnects cannot provide the required performance, scale, and bandwidth to keep up with AI demands. So UEC aims to address these concerns by adding new capabilities to the known and proven Ethernet technology. By adding a number of new features and capabilities. There are multiple working groups. So UEC actually have a bunch of different working groups. You can see a couple of those here, the physical layer, link layer, transport layer, software layer. And they just actually released the first spec, the UET, the Ultra Ethernet Transport Spec version 1.0, defining basically how to replace the RDMA part. And as I said, I'm going to touch on RDMA and Rocky a bit later on in this presentation. So kind of looking at the topologies, and once again, this is truly high level fly through here, but the AI data network could consist of the front end and the back end network, where the front end network have things like connect your inference cluster, your shared storage pool, your WAN connectivity, your internet connectivity, your data center interconnect, your web server, so on and so forth. So you see that you basically have multiple services connecting into this network. Northbound, you have all the connectivity to the outside world. And you could also connect your management network for your training jobs here. Now, for the backend part, this is the GPU compute fabric where you interconnect your GPUs. And you would have a dedicated storage fabric as well. You could converge the compute with the storage fabric here. That's also up for debate. How do you want to actually build it? Now, this is a pretty technical slide. I try to keep it on a high level, but I think it's key to kind of understand when we start to talk about, the lossy nature by Ethernet moving into a lossless nature. So InfiniBand uses direct memory access, DMA, which basically accesses the memory directly from the NIC and relieves the CPU from the intense memory access work. So RDMA, which stands for Remote Direct Memory Access, is the basis for InfiniBand, which makes the network fast since it can transfer the data from one memory to another memory without taking up CPU cycles. So RDMA is a key technique to reduce end-to-end communication latency between multiple machines and GPUs, as RDMA allows host to access the memory of another host directly by bypassing the OS kernel. So as Ethernet is the most popular protocol, as we have kind of discussed here already, and it's widely adapted by data centers, Mellanox came up with the Rocky, so RDMA over converged Ethernet, which is basically encapsulating RDMA traffic into Ethernet headers. So this is kind of a chart just comparing InfiniBand, Rocky V2, and Ultra Ethernet. I'm not going to go through this line by line, but I think it's key to kind of understand that you talk about something called DCQCN, which stands for Data Center Quantized Congestion Notification, which is an end-to-end congestion control scheme, including things like PFC and ECN, so priority flow control and explicit congestion notification, which are mechanisms in place for basically dealing with control of AI traffic. Once again, referring to the fact that moving from a lossy to a lossless media, or using Ethernet as the media, how you basically want to use it as a media. Uh, so compared to expensive network deployments like InfiniBand, Rocky is a relatively cheaper option, although it cannot be considered inexpensive per se. Now, as I kind of alluded to the fact that you have various kind of sorry, actually, this is the IP fabric, so my bad here. So according to Ericsson's mobile network traffic, it could hit 472 exabyte monthly by 2030. 473 exabyte. Think of the amount of traffic. And as demand for seamless high-speed connectivity grows, CSPs are under pressure to find ways to efficiently manage this data and deliver reliable, high-quality 5G connections to the end users. So to optimize network traffic, many CSPs, so communication service providers, are now deploying scalable, high-performance network fabrics in their data centers to support cloud-native 5G applications. And I'm reiterating, cloud-native 5G applications. Such applications run on bare metal servers using cloud-native technologies like Kubernetes and cloud-native DevOps principles, where automation and orchestration of such fabrics and workloads are an integral part of the solution. Now, as highlighted, cloud-native 5G workloads, meaning that 5G is the first generation of a cloud-native mobile network. This means that all services run on compute and not anymore on purpose-built appliances and hardware. So think of this. you basically have latency sensitive radio traffic. You have truly latency sensitive traffic that you move over to an Ethernet infrastructure. As said, everything is running on compute. It's cloud native, which basically means that you then start to build various size of fabrics. You could go to an edge fabric, as you can see, in this illustration. If you look at the left-hand side, you basically have a two-node construct. Think of that as an edge fabric, a microfabric, or a micro data center, which you could scale up to a true CLOS architecture, 3-stage or 5-stage, going from two-node to multiple nodes, spine leaf architecture, super spine and leaf architecture. So a high level kind of architecture picture here. This is for the obvious reference design for the front end network. And this is just to give you an idea of the principles here. So the characteristics of the front end data center fabrics are CPU to storage traffic 25 or 100 gig connectivity, and CPU north south traffic 100 gig or 200 gig, with possible some oversubscription ratio on leaf spine connectivity. So you can oversubscribe this network. 1 to 2, 1 to 3, that's still okay-ish. While if you look at this one, which is the backend fabric. So characteristics of backend AI data center fabrics are CPU to storage traffic front end to backend 2500 gig, and GPU to GPU could be 100 gig, 200 gig, or 400 gig, with GPU to storage backend traffic 100 gig, 200 gig, and CPU north south traffic 100 gig, 200 gig. And key thing is no oversubscription. Everything needs to be wire speed. As you basically can see in this diagram, everything is 3.2 terabits here. No oversubscription. Once again, kind of hitting the latency issue that you have with AI workloads, the job completion time that I touched on briefly. So I guess you guys can kind of realize and appreciate the fact that once you start to run AI workloads, it's going to change fundamentally how you build your AI data centers. Now, obviously, building an AI data center or running AI workloads is much more than just kind of the fabric itself. Think of the fabric as, for the lack of a better word, the plumbing connectivity. So you have multiple layers, and I picked, just kind of some of the logos acting in the different layers here. But on layer one, you have, this is the compute and foundation model layer that contains the foundation models themselves, as well as the infrastructure to train, fine tune, optimize, and ultimately deploy the models. Layer two, that's the data layer containing the infrastructure to connect the LLMs to the right context, wherever they may exist within the data system's core components, including data pre-processing, data pipelines, databases, metadata, data store, and context caches. Layer 3, this deployment layer contains the tools that help developers manage and orchestrate AI applications, and includes agent frameworks, prompt management, and model routing and orchestration. And then the final layer is it contains the solutions that help monitor runtime LLM behavior and guard against threats, including new categories for LLMs, observability, and security solutions. And then you basically have the network part here as well, which kind of is layer one-ish or below layer one. So this kind of concludes a high fly through on some of the challenges for AI workloads and the myth around AI networks and AI4 networks. I hope you kind of got the message here that AI is coming. It's just a matter of everybody getting on the bandwagon here. It's something you need to start to consider today. It's quite multimodal in the sense that AI can be used for so many different things.